The next problem is, in natural water, hardness is mainly caused by calcium and magnesium, calcium and iron, calcium, sodium and potassium, calcium and magnesium, here is calcium and manganese. So, the hardness is mainly caused by calcium and manganese. Calcium and magnesium, which is the option D. So, next problem. The theoretical oxygen demand of a 0.001 mole per liter glucose solution is. So, the theoretical oxygen demand that we have earlier studied, that it is the oxygen demand that is calculated from the chemical reaction. So, here they are asking to find the theoretical oxygen demand of 0.001 mole per liter glucose solution. So, 1 mole of glucose combines with 6 molecules of oxygen. If you are looking at the equation which we have studied earlier in the theoretical oxygen demand, C6H12O6 plus 6 oxygen molecules combines together to form CO2 plus H2O. So, 1 molecule of glucose combines with 6 molecules of oxygen, or 6 moles of oxygen. Therefore, 0.001 mole per liter, which is the one given in the question, 0.001 mole per liter of glucose requires, we have to multiply the right and left hand side with 0.001. 1 mole requires 6 moles of oxygen, so 0.01 will require 6 into 0.001, which is 0.006 mole per liter of oxygen. Now, there is a formula to find the number of moles, which is equal to the weight in gram divided by the molecular weight in gram. Now, the molecular weight of oxygen is 16 atomic weight into, there are 2 atoms. So, 16 into 2, that is 32. So, the molecular weight is 32 and the number of moles, we know it as 0.006 mole per liter of oxygen. So, we know the number of moles, we know the molecular weight. Then we can find out the weight of the sample as 0.006 into the molecular weight 32, which we will get the answer in gram. So, we will convert into milligram. Since the answer here is given in milligrams, we can multiply by 10 raised to 3 so as to convert it into milligram per liter, which is 192 milligram per liter. That is option B. Then the next question, the results of analysis of a raw water sample are given below. Turbidity 5 milligram per liter, pH value is 7.4, fluorides is 2.5, total hardness is 300 milligram per liter, iron is 3 milligram per liter, and MPN, that is the most probable number, is 50 numbers per 100 ml. Now, from the data given above, it can be inferred that the water needs removal of A. turbidity followed by disinfection, B. fluorides and hardness, C. iron followed by disinfection, D. fluorides, hardness and iron followed by disinfection. So, here we have studied the limits for all of these parameters. So, when you are looking at it, the pH value, we have studied that it should be, for drinking water, should be between 6 to 8.5. So, pH is correct. Fluorides should be in the range of 1 to 1.5 milligram per liter. So, but here we can see that the value is higher. So, again, there should be some technique by which this fluorides is removed. So, fluoride removal is required. Then the total hardness is 300 milligram per liter. This value, the total hardness which is good for consumption, is very much less than this 300 milligram per liter. So, again hardness treatment should also be carried out. Then the iron quantity, the amount of iron that can be present in the water is around 0.3 milligram per liter maximum. So it's 3 milligram per liter, hence iron should also be removed. And also next is the MPN, that is the most probable number, that is there is 50 units per 100 ml, but actual value is of most probable number is there should not be any bacteria present or a maximum of 1 bacteria present, but here it is 50. So we have to do disinfection also. So these 4 processes must be carried out, that is fluorides, hardness treatment, iron, and followed by disinfection. So option D is the answer. The next problem. The results of a water sample analysis are as follows. Cation, here its concentration and their equivalent weight are directly given. Sodium, concentration in water sample is 40 and its equivalent weight is 23 of sodium atom. Magnesium, its concentration in water is 10 and its equivalent weight is given as 12.2. Calcium, it's 55 milligram per liter and the equivalent weight is 20. And potassium, the concentration in water is 2 and the equivalent weight is given as 39. So here, in order to convert, here everything is given in milligram per liter. Now here they have also given a conversion of milli equivalent weight of CaCO3 is taken as 50 milligram per milli equivalent. Now the hardness of the water sample in milligram per liter in terms of CaCO3. Always the hardness is expressed in terms of CaCO3. Also alkalinity and acidity also is expressed in terms of CaCO3. So what is the hardness of the sample as expressed in terms of CaCO3? So the total hardness, earlier itself we have used the formula, is equal to magnesium concentration equivalent weight of CaCO3 by equivalent weight of magnesium plus calcium or concentration of calcium into equivalent weight of CaCO3 by equivalent weight of calcium. Equivalent weight of CaCO3 we have in earlier problems we have found out that it is 50 and that of magnesium it's 12. Here also equivalent weight of CaCO3 is 50 and equivalent weight of calcium is 20. Now in the question here directly all these values are given. For calcium the equivalent weight is magnesium 12.2 and calcium is given as 20. So we need to substitute that is why it's 12.2 here. It's directly given. Otherwise if it's not given we assume it is 12. Here it's directly given. Now the concentration of magnesium that is present is 10. That is the one we are writing, 10 into 50 by 12.2 plus concentration of calcium. So magnesium and calcium are the hardness causing ions. So calcium that is 55 into 50 divided by 20. You will get the answer as 178.48 which is approximately taken as 179. So the option C is the answer. Now the next problem, that is the common data for questions, this one and the next one. So a water treatment plant treating 10 mld or 10 million liters per day of water requires 20 milligram per liter of filter alum or Al2SO4 thrice .18H2O. That is the chemical formula of alum. The water has 6 milligram per liter of alkalinity as CaCO3. Now the atomic weights of aluminium, sulfur, aluminium is equal to 26.97, sulfur is 32, oxygen 16, hydrogen 1, calcium 40, carbon 12. Now they are asking you to find the total alkalinity requirement in 10 raised to 6 milligram per day as CaCO3 matching the filter alum. So they are just asking you to find the total alkalinity that is required. Now before that, in order to do this problem, first of all you have to understand what is the chemical reactions taking place when alum is being added to the water. So this alum, that is Al2SO4 thrice .18H2O, on reacting with calcium bicarbonate that is present in the water will give you calcium sulfate plus aluminum hydroxide, which is the precipitate formed or the flock that is formed, which will settle to the bottom, then carbon dioxide and water. Now here the molecular weight of all these are given. Aluminum is given, sulfur is given, oxygen is given. So the total value, when you add all this, you will get it as 666. That is, how will you calculate? 2 molecules of aluminum are there. Aluminum, it's 26 point. So aluminum, if you are, this is the formula of alum, and if you are calculating the molecular weight, 2 atoms of aluminum, that is 26.97, plus how many atoms of sulfur are there? 3 atoms. So 3 into 32 plus, now look at oxygen. How many oxygens are there? 3 into 4, 12 oxygen atoms are there. So 12 into value of oxygen, atomic weight is 60, plus again how many hydrogens are there? 18 into 2. Number of atoms of hydrogen are there, and the valency of hydrogen is 1, plus oxygen, how many oxygen atoms are there? 18 oxygen atoms are there. So 18 into oxygen molecular weight is 16. So this we get the total as 666. So that is what is they have written here as 666. Now similarly, if we substitute the values and find that for calcium alone, but here in order to balance it, we have written a 3. So that is this 3 into CaHCO3 twice the total molecular weight, we obtain it as 162 when we are adding this. So 3 into 162 is the total grams of calcium bicarbonate that is used. Now this calcium carbonate that is present in this water sample will react with water and carbon dioxide so as to form this calcium bicarbonate. That is the bicarbonate that is reacting with the alum and producing the aluminum hydroxide, calcium sulfate, etc. So from the equation 1, we can see that 666 grams of alum can neutralize 3 into 162 grams of calcium bicarbonate. This calcium bicarbonate is responsible for the alkalinity of the water sample. So 666 grams of alum requires 3 into 162 grams of calcium bicarbonate or alkalinity. Again, so in order to calculate the total alkalinity, again one more thing is there, that is 3 into 162 gram of alkalinity is equivalent to 3 into 100, that is CaCO3 value is 100. So here they are saying 3, this is the molecular weight of calcium bicarbonate. So when this reaction occurs, there are 3 molecules of calcium bicarbonate combining with the alum. So if we are balancing this, we can add a 3 both here and here. Since there are 3 molecules, we are adding a 3 here also. So in order to balance it, we have to add a 3 here, calcium, and the remaining. Now we will be considering these 2 only. So there will be 3 calcium atoms on either side. Carbon, we also have to balance the remaining ones. Now here we can see 3 atoms of calcium carbonate. So there is 3 into 100. 3 into 100 grams of calcium carbonate is required so as to form 3 molecules of calcium bicarbonate, which in turn is required for alum. So we can directly say that 666 grams of alum requires 3 into 100 grams of calcium carbonate. So let me write it here. 666 gram of alum requires 3 into 100 grams of calcium carbonate. Now the total alkalinity required is equal to 3 into 100 divided by the 666 into the dosage of alum that we are providing. Here in the question, 20 milligram per liter is the dosage of alum that we are giving. So alkalinity required is equal to, this is an important conversion, alkalinity of the alum, alkalinity required is equal to 3 into 100 by 666 into the dosage of alum. So substituting the dosage of alum, which is given in the question as 20 milligram per liter, we get 3 into 100 by 66 into 20. That is the total alkalinity of filter alum in terms of CaCO3 for water requiring 20 milligram per liter of filter alum. That we get it as 9. That is the alkalinity required. Now in the question they are asking us to find, this is the unit is 9 milligram per liter. Now they are asking us to find the units in this much 10 raised to 6 milligrams per day. So for that, the total alkalinity required, this is in milligram per liter. Now what is the total, this is for 1 unit of discharge, 9 milligram per liter, or for 1 liter water sample 9 milligram per milligram is the total alkalinity required. So for total, how much quantity of water is there? 10 mld. So for 10 mld, I have earlier told milligram per liter multiplied by mld, you will get the answer directly in kilogram per day. So then this here in this case 9 milligram into, the question is given 10 mld. So 10, you will get it as 90 kilogram per day. But in the question it is given as, you have to represent in terms of 10 raised to 6 milligrams per day. So to convert kilogram to gram, we have to multiply by 10 raised to 3. Again we have, in order to convert it into milligram, we have to multiply by 10 raised to 6 milligram per day. So the answer is, they are asking us to represent it in terms of 10 raised to 6 milligrams per day. So 90 into 10 raised to 6 milligrams will be the answer. So 90 is the answer that we have to find out. That is option C. Now similarly, they are asking us to find the quantity of cooked lime required, again in 10 raised to 6 milligram per year as CaO. So in order to calculate the quantity of cooked lime, again we have to look at this formula. This calcium carbonate on decomposing will form calcium oxide plus carbon dioxide. Now calculating the molecular weight of CaCO3, we get it as 100, and that of CaO is calcium is 40, oxygen is 16. So total CaO or the cooked lime is 56. Now the natural alkalinity that is already present in the water is given as 6 milligram per liter of alkalinity is already present in the water. But the alkalinity that we require, we have found it out, find it as 9 milligram per liter. So alkalinity already present in the water is 6. The alkalinity actually required is 9. So extra 3 milligram per liter is required. So that is given by this cooked lime. So natural alkalinity available in water is 6 milligram per liter. Total alkalinity required to be added in the form of cooked lime is 9 minus this 6, that is 3 milligram per liter extra alkalinity is also required. So now we can say 100 grams of CaCO3 will give you 56 grams of CaO. So the quantity of CaO required to produce 3 milligram per liter of CaO by, so 100 grams of CaCO3 produces 56 grams of CaO. So 1 gram of CaO or the quantity of CaO that is required, quantity of quicklime required, quicklime is also known as CaO, is equal to 56, which is the molecular weight of CaO, divided by the molecular weight of CaCO3, 56 divided by 100 into alkalinity that is deficient. Alkalinity deficit, that is by how much the water or how much more alkalinity is required to be added in the form of quicklime so that the total alkalinity reaches 9 mg per liter. This is an important formula that is used to find the quantity of quicklime. That is equal to, always it's 56 by 100 into the alkalinity deficit. Here the alkalinity deficit, that is the extra alkalinity that has to be added in order to bring the value to 9, is 3. So 56 by 100 into 3. That will give you 1.68. That is for 1 liter of water, it's 1.68. So for total, how much? 10 mld. For 10 mld, we have to find as 1.68 into 10 mld. So here that is 1.68 into 10 mld. We directly get the answer in kilogram per day. But here in the question they have asked us to find per year and not per day. So again 1.68 into 10 and we require the answer in milligrams. So converting kilogram to milligram into 10 raised to 6 milligram. Now in order to convert a day into a year, we have to multiply by 365. That is into 365. That will be the final answer that we get. It as 6132 into 10 raised to 6 milligram per year. So this is the answer that we require, 6132. That is the answer. Hope it's clear. Now in the next problem, most of the turbidity meters work on the scattering principle. The turbidity value so obtained is expressed in which of these following unit? That is the lights based on light scattering principle. It is the unit that we are using it to express it is FTU or Formison turbidity unit. That is the only instrument that is working on scattering principle. Next one, hardness of water is directly measured by titration with ethylene diamine tetraacetic acid or EDTA using A. Areochrome black tea indicator, B. Ferroin indicator, C. Methyl orange indicator, D. phenolphthalein indicator. Here for hardness test, always for EDTA is the titrant and Areochrome black tea indicator is the indicator that is being used. So that is the answer for that. Now the organism which exhibits very nearly the characteristics of an ideal pathogenic indicator is Entamoeba histolytica, Escherichia coli, Salmonella typhi, Vibrio coma. So what is the indicator organism? That is Escherichia coli. Now next question, a standard multiple tube fermentation test was conducted on a sample of water from a surface stream. The results of the analysis for the confirmed test are given below. So the sample size is 1 ml, 0.1 ml sample is taken, then 0.01 ml sample is taken, and we are testing it, placing it in 5 test tubes and testing it, and number of positive results out of the 5 tubes. For 1 ml sample, 4 of them turned out to show positive results, that is the presence of bacteria, and 0.1 ml 0.1 ml also we have taken 5 tubes and the 3 of them became positive and 2 became negative. Then the sample size of which was diluted to 0.01 ml, that also 5 test tubes were taken, out of which only 1 turned out to be positive and the rest all turned out to be negative. Now The MPN index and 95% confidence limits for the combination of positive results were 5 tubes used per dilution for 10 ml, 1 ml and 0.1 ml. So, this is the combination of positive and MPN index per 100 ml and 95% confidence limit. Using the above MPN index table, this is the MPN index table, the most probable number or the MPN of the sample is found out as. Now, when we look at the sample size here, there is 1 ml dilution, 0.1 ml dilution and 0.01 ml diluted waste sample tubes are taken. The positive result combination is 431, that is for 1.1, 0.01. So corresponding to 431, here the value of MPN that we get is 33. But this particular MPN index table is given for the dilutions 10, 1 and 0.1. It's not 1, 0.1 and 0.1. That is, the whatever value we have to obtain here, we have to multiply by 10. That is, this is a 431 combination, and corresponding to 431 combination we got 33, and this 33 into the index table here, MPN index table is drawn for 10 ml. If you are multiplying this by 10 ml, then it becomes corresponding to that table. That is, this becomes 10, this becomes 1 and this becomes 0.1, which is same as this. So, in order to get the correct value, this value that we obtain corresponding to 431 result, that into the 10 that we have to multiply here, we'll get it as 330, which is the answer for this.